Hi there. For this section, N10, we're going to be looking at terminating and recurring decimals. Two types. So, for the basic foundation element, you simply need to be aware that some decimals are terminating, and so, for example, we might have 0.5. That's it, just 0.5, it stops. What about 0.1738? So the point about them is that they come to an end. There is a limited number of digits after the decimal point, and it doesn't really matter how many there are. There could be 1,000 digits. If they come to an end, it's regarded as a terminating decimal. The other type is the recurring decimal. Now you may be able to work out, if you don't know already, from the word, that a recurring decimal recurs or continues on and on and on. And so everyone's seen on the calculator when they divide, say, 1 by the number 3 or something like that, they'll get an awkward number, so you get a recurring decimal. So you might have something like this. You might have 0.99999 and so on, and it just goes on and on and on. In fact, it fills your calculator and obviously can't go any further. But you know, if the calculator was, say, a mile long, the display on it would show, like, you know, thousands and thousands and thousands of nines. It goes on, and of course it's a bit stupid, isn't it, to be writing hundreds of nines. If we just want to say this 9 carries on forever, then we would just write 1 9 and then just put a little dot above it, and that tells the person looking at it that the 9 goes on forever. You can also have, let's say you had 0.16 and the dot was there, so of course that would be 0.16666 because it's the 6 that is recurring. If you had, let's say, 0.25, and this time there's a dot over the 2 and the 5, that tells us that both of these numbers recur. So this one would look like 25, 25, 25, and so on. Get the idea? And if there are more than 2 numbers that recur, then rather than put dots over a lot of them, we can do something like this. We have a dot over this one and a dot over that one. It means that everything in between, those included and everything in between, all recur. So you get 0.1276, 1276, and so on. So this is the notation that we use for denoting a recurrence in some digits. Okay, let's just get rid of this, and just want to say something brief about, while we're on the subject, something brief about corresponding fractions. And by this I mean that if we have a fraction like 7 over 2, you put that into your calculator, you would get an answer of 3.5. And a terminating decimal like this one can be represented as a fraction with a whole number on the top and a whole number on the bottom. And you may have seen some others, like say 3 over 8, which I think is 0.375. You can check that on the calculator and tell me off if I'm wrong, if I remember that wrongly. Okay, but again, it's a terminating decimal, and it can be represented as a fraction with an integer on the top and an integer on the bottom. There are a few of those you'll come across from time to time. You will see 3 over 2, and eventually you will come to recognize these and know what the equivalent decimal is. And really, there's no requirement to memorize a certain set of these, but rather just to be aware that they have corresponding fractions, these terminating decimals. So let's have a look at something different now. When we move on past the foundation requirements for this section, we come on to the subject of how to convert a recurring decimal into a fraction. So it turns out that we can, even with recurring numbers, they too can be represented as fractions with a whole number on the top and a whole number on the bottom. There are exceptions that are irrational numbers, so-called. We can't really express them as a fraction very accurately. So for example, pi, that big long number, famous for going on forever, you know, so on. Well, pi, because of the nature of it, unfortunately it can't be represented very accurately, or rather not completely accurately. Now 22/7 is good enough for most things as an approximation of pi, but let's get back to what we were originally talking about, which is the case of a recurring decimal, say like 0.7. How can we convert that into a fraction? Now going the other way might be okay. If I had a number like, I don't know, 8 over 90 or something like that, I could, which is an example of a recurring decimal that's been made into a fraction. I can just plug that in the calculator, or do it, you know, with the bus stop method. You know, do a little division, you know, at the bus stop where you divide it like that. So we can do that, but going the other way is a little bit more involved. So we'll just have a look at the method we use to get this into a fraction then. So what I'd advise you to do is this, and there's more than one method, but here we go. I would use the letter x and assign to that letter x this thing here. So we are just getting down on paper that we're letting x equal the recurring decimal. What we do then is we need to find a multiple of x, either 10x's or 100 or 1,000 or 10,000. Some multiple like that of x, which will give us a recurring element here, which is the same as this one. Now watch what happens when I just simply write down 10x. So if that's x, what will 10x be? Okay, well, if we wanted to multiply this number here by 10, we could just move the decimal point one place to the right, and what will that give us? Well, it will give us 7.7 recurring. Why is that? Well, remember that this here is 0.7777. So, and it goes on. Okay, so if we were to just move the decimal point and put it there, these look like 2's, don't they? I'm aware of that. Okay, so we get 7.7777 or 7.7 recurring. Okay, so what was formerly a recurring digit has now just become a normal digit, and so that's where we get this from anyway. Okay, so what was the point of doing all that? Well, it turns out that we can do a subtraction. We can do our 10x minus our original x, and I'm going to write on the right hand side here the equivalent numbers. So 10x was 7.7 recurring, and we're going to subtract x, which was 0.7 recurring. Now look what happens in the next line. 10x minus 1 by minus x, or 10x minus 1x if you prefer, becomes 9x. Look what happens on the right. It's almost unbelievable that this works, but when we have 7.7 recurring minus 0.7 recurring, it turns out that this recurring bit minus this recurring bit, now even though it goes on forever in both cases, they are exactly the same thing. And so by logic, if we take one from the other, no matter how big it is, it goes, it disappears, it becomes 0. So we end up, having done the subtraction, with just the number 7. Okay, so everything after the decimal point on the first one and the second one, they cancel each other out. We've got 9x equals 7. You may remember from your rearranging of your formulas and your equations that we can isolate this x on the left here by dividing both sides by 9. What does that do? Well, on the left it creates a fraction with a 9 on the top and a 9 on the bottom, which cancel each other out. If you prefer, 9 goes into 9 once, 9 goes into 9 once, so you end up with 1 times x, which is just x divided by 1. So x divided by 1 is just x. So really, we wouldn't even need to write those ones in. If I tidy this up, look what we've got. We've now got x equals 7 over 9. And so we've converted, haven't we? We've converted our original recurring decimal to its equivalent fraction. If I told you that, let me get rid of this again. If I said that, okay, we've said that 0.7, let's be consistent here, Paul, black, 0.7 recurring becomes 7 over 9. You may sort of be able to work out that if I had 0.8 recurring, just think back at the working out we did. We'd end up with 8.8 recurring minus 0.8 recurring, which would just leave 8. And that would also be over 9, okay. 0.2 recurring, guess what? 2 over 9. So, now although for the purpose of answering an exam question you do need to do the working out we've just seen, so you need to go back over that working, and if it's not clear, look for other resources on YouTube or elsewhere or in textbooks which may be able to explain it better than I have. But that working out will be required when you're answering an exam question, so you do need to know it. So I thought I would mention this sort of pattern because it will crop up again in a moment when we do some more complicated ones. So let's try one of those right away. If we had 0.23 and both of these things are recurring, okay, what did we say we do? Step 1, we let x equal our starting decimal. Now look, we said that we needed to think of a multiple of x which has the same thing on the right hand side. Now look, 10x is no good. What would happen with 10x? If I move the decimal point, from here to here, I'm going to end up with 2. I'm going to end up with 2.3232323. So it would end up like this. Whoops. Get rid of that. It would end up with 2.3, then 2323, and so on. Now it's recurring, all right, but look here. We've got 0.32, not 0.23. We need the same on the right-hand side. So what are we going to do? Well, it turns out that we said we can use a multiple. We're going to use a different multiple. We're not going to use 10x after all. we're going to use 100x. So if you now imagine what happens, well, we're going to go 10 times another 10. Okay, so multiply by 100, we move the decimal point twice to the right. So on the left now of the decimal, our new decimal point, on the left we just have 23. We have our decimal point which we just moved, and what's going to come after it? Well, if we remember that this number was 2323, remember? And so what's going to come after it when the decimal point goes to there and then to there? We're going to have 23.23. 232323. So we've got our recurring bit. Now, of course, what's interesting is that on the right hand side of this one and the right hand side of the decimal point on this one is the same. It's both 2, 3 recurring. Okay, so why did we do that? Remember before, so we could do the subtraction. So we're going to subtract this. We're going to take this. We're going to take this and subtract this from it. Okay, so 100x minus x itself. So 100x was what? 23.23 recurring, minus x, the original x, which was just 0.23 recurring. And we said that what happens on the left? Well, this time it's 100x minus 1x, which is 99x. And that is equal to what's on the right hand side. Now remember what happened. The bit after the decimal point, in each case, they cancel each other out. One is subtracted from the other, leaving 0. So we end up with just our 23 minus 0, which of course is just 23. And using our method of dividing both sides by the number that we don't want on the left there, we want x by itself, so we need to get rid of 99. So we divide both sides by 99 like that. Yeah, so what do we end up with? Whoops. We end up with x equals 23 over 99. Like before, if I told you that, bearing in mind that 0.23 recurring becomes 23 over 99, you might see a pattern, and you'd be doing well to spot this pattern here. If I told you that not 0.23 but 0.78 recurring becomes 78 over 99, you're beginning to see a pattern. 0.24 recurring becomes 24 over 99. And I mention that now because later, after we've done a couple of harder ones of these, I'm going to mention to you something, a bit of a tip for you, which will help you in your work and in your exams. And it's to do with spotting this pattern where the number recurring ends up on the top of a fraction. And on the bottom we seem to have either a 9 or a 99. Okay, so this is something we'll mention later, but for now we'll use we'll have a look at another example, because they're not always like that. I mean, the recurring ones could be like this. Oops. Let's say you had 0.17. Now this time only the 7 is recurring, so that number would be 0.17777 and so on. What are we going to do with this one? Okay, well let's have a look what we do. Start again. Let x equal the first number. We need to think now, don't we? How are we gonna do this? Well, look, here's a bit of a problem. If we just multiply by 10, we end up with 1.77. that is not the same as what we have here. Okay? If we multiply by 100, we get 17.77. And that's still not the same. You might be thinking, well, we've got a problem here, because no matter how many times we multiply this number, it's never going to have another 1. There's no 1s left. So what are we going to do? This is why this one is so unusual. You have to have a different strategy. Really, what we're looking for are two multiples of x. Two multiples of x where we can perform a subtraction. Now, up to now, we've used the original x decimal, haven't we? And we've just found a multiple of that for the other. But you know, we don't have to stick with just plain old x. We can start with a one multiple and subtract another multiple, and it might not just be a plain old 10x. Look what happens when if I write out what 10x would be. Well, we've just said what 10x would be. We move the decimal point once to the right, not original number. We get 1.7 again. But if we remember what we said about 100x, if we move the decimal point once, twice, we end up with 17.7 recurring. Now, what's happened is we've now got our 7 recurring on the right hand side of the decimal point for both of these. Okay, so this is why this example is different. We are using this time 100x, and we're going to subtract not x but 10x. What will that give us? Okay, well, our 100x we said above was 17.7 recurring. We're going to subtract 10x, which was 1.7 recurring. And what happens? Well, this time on the left, it's 100x minus 10x, which is 90x. That's going to equal to, well, on the right hand side, the recurring bits cancel out. This time, we have something different. We have a 17 minus 1. Okay, so we now have 16. And through our employment of our skills in rearranging this this last line, we end up with x is equal to 16 over 90. So we've gone from there to this one. Now, just continuing the note I made a few moments ago about this pattern that you may see in these calculations, we seem to end up with, on the bottom, either 9s or 0s. So we have like in the previous one we had 99. The one before that was just 9. This is 9 and the 0. And to be honest, they all end up with a 9s or 0s on the bottom. Different quantities on them. And on the top, well, up to now, we've had the original number, the recurring number, except, if you think about it, this original one was not 1, 7 both recurring. This one was in fact just at the 7 recurring. Okay? So this is why our number on the top is not exactly 17, it's different now, it's 16. And like I said, I did promise that I would tell you how we can quickly know what the fraction is going to be based on what we start with. But that's a bit of a cheat. So you must not tell your teachers, oh, I went on the internet and Paul from Wirral Maths Tuition told me to do this, because your teachers will come and hunt me down for breaking the rules of maths. The truth is, folks, that when you get a question like this, you will have to do the full working out to show your understanding of how we got there. So any shortcuts I tell you will have 2 values, which I'll try to explain to you now. if we had, say, let's think of an awkward number, 0. Let's think of an awkward one. Well, no, we'll just pick that one. Now, I said earlier that 0.719 with a dot above the 7 there, and a dot above the 9 there, means that all 3 digits there, the 7, the 9, and anything between, is included in the recurring number. So this would be, like I say, 719, 719, etc., etc. Okay. Now, what I'm going to do is, just on the right hand side, I'm going to show you what the fraction, what the answer is going to be, and we're going to work that out very quickly. But like I say, that doesn't count as working. This is just for your benefit. So just over here, what I'm going to do is, I know that because all the digits are recurring on the right hand side, I actually know that the fraction is going to have 719 on the top. And the other thing I know is, because all 3 digits are recurring, then at the bottom of this fraction on the right, I put a number 9 for each of those recurring digits. So 3 recurring digits means 3 9s. Okay? So that actually is the answer. But we've got to be careful. That is only there to help us. And I said it helps in 2 ways. How does it help? First of all, in a minute when we do the proper working out, we're going to check our answer with this one and see if it corresponds. So that's the first use. The first use of this is that it is a check on our answer. The second one, which you might find in some cases really useful, is that if you knew these a little bit more, well, then you would remember where we would get that 999 from. If you think about it, the 999 comes from a subtraction on the left, a subtraction of x's. So we've had 10x minus 1x, we've had 100x minus 10x, we've had all these things. So if you think about it straight away, this 999 tells us that the subtraction must have been based on 1000x take away 1x. How else would you get the number 999? It comes from 1000 take away 1, which means that over here we know straight away which multiples of x we're going to need. Now you could go through this and work it out, and some young people seem to prefer that. That's okay. If you're that good, then I'm very pleased. But for most people, they need a bit of help with this, and so from that quick calculation on the right, we're able to get these 2 multiples of x straight away. So we actually know that we can use x itself, 719, and then we've got 1000x. So how do we find 1000x? Well, we just move that decimal point, don't we? We can just say 1000x is going to be 1, 2, 3. So 10, 100, 1000. So it's going to be 719 point. 719 point. 719 point. 719. Like that. Okay. So if you're not sure what's happened there, just go back and have a look. It is straightforward. We've just moved the decimal point. But isn't it great that we've got these two multiples of x. We know what they are straight away. We don't have to guess, we don't have to work it out, because the number told us. And now we can go straight in and do our subtraction. So we've got 1000x, take away 1x. Well, we write down what 1000x is. It was that. And we're subtracting our normal 1x, which is 719. There we go. We know what happens on the left. 1000x minus 1x is 999x. That is equal to, on the right, we have the recurring bits, of course. Again, we have the recurring bits all nicely disappearing, and so we just have 719 there, take away 0. If it helps, you know, you can, there's nothing stopping you if you must. You can do this, you know, you can do this and, you know, do the subtraction like that, you know, the way you do when you're doing normal subtractions. You can do it that way if you want. So on the right hand side now we simply have 719, and by manipulating that we end up with, of course, x equals 719 over 999. Hey, we're not surprised, are we? We're not surprised we got that because we added up there. But we know that helps us really to be confident that our answer at the bottom is correct. So I said there were two uses, didn't I? I said there was two uses for this. This is getting a right mess now, isn't it? Look. I said there was two uses for doing that quick calculation. One is to check your answer. Two is to tell you over here which multiples to use. Okay. So maybe if we finish off by just doing, we'll just maybe do one more. Don't you fall asleep on me? No one falls asleep in my class. Here we go. I'm making this up as I go along, you know. These numbers. I hope it works. 0.2. Okay, there's one that we haven't really seen before. Well, you can maybe guess what I'm going to do on the right hand side. Well, you may be expecting me to do 275 over 999, but not so. Why not? Why not? Because, well, a few reasons. Well, the first thing is there are only two digits that are recurring. That's the first thing, and that affects a couple of things with this fraction over here. The top goes like this. It is 275, that's the whole number, so we write the whole number out. But we must remember to subtract any non-recurring numbers. So of course we've got a non-recurring number there, haven't we, after the decimal point. So that's the top sorted now. So that's the rule, really. So if they were all recurring, they would all go on the top as they are. But if there's any non-recurring numbers, we need to subtract that from the whole thing. So 275 minus 2 on the top. And what do we do on the bottom? Well, for each recurring number, we put 9s. Okay, so we have one recurring number there and one there. So we have two recurring numbers, we have 2 9s. And for the non-recurring one there, no dot above it, we put a 0. Okay, so what do we end up with? We end up with 273 over 990. Okay, so there we go. We've got, within just a few seconds, we've got our answer. We just need now, unfortunately, to go and do the donkey work on the left. Great thing is, because of this, 990. How do I get 990? Well, it's 1,000 take away 10. So there's my two multiples straight away. Okay, so if x is equal to 0.275, 0.275, and those two are recurring, then 10x will be 2.75 recurring, and 1000x, 1, 2, 3, will be 275.75 recurring. If you're not sure how I did that, as I say, go back, take it slowly. On the left in our subtraction, we have 1000x. We're subtracting this one, 10x. And on the right, well, we just stick the numbers in, don't we? Seems very long-winded, this, but this is the type of thing we have to do. 2.75 recurring. So on the left now we have 1000x minus 10x, which is 990x. And you're starting to see it all fall into place, aren't you? Yes, you are. What happens on the right? again, the recurrent bit and this recurrent bit, one's subtracted from the other, they happily just vanish away. What about the actual other numbers? On the left of the decimal point we've got 275, but this time we've got to take away 2. So 275 minus 2 is 273. And that's it. Remember, the recurring bits have gone. And once again, to finish off, by manipulating this equation, we end up with 273 over 990. Okay, so just to remind you, this is what we predicted. And why did we do this thing? It helps us to check our answer, and it tells us which two of these multiples to use straight away without any working out whatsoever. So that's the benefit of it. Okay, so I'm just going to try and recap then. So just go back through the video to learn the standard way of changing any recurring decimal into a fraction. So we've got that, but regarding that tip I gave you, just remember this. So we have on the top, we have the, I'll write it out in words. So if you're doing the quick fire way of getting the answer straight away, well, on the top we want everything. This is the first thing. Everything after the decimal point minus any non-recurring numbers. Ugh. And then we're going to say that that's on the top of the fraction, and on the bottom we're going to have 9s for each recurring number and 0s for any non-recurring number. Hope you can read that awful writing. Okay, so remember the examples we used. So we have, say we have 0.376, and maybe it's just the 7 and the 6th that recurs. We can say everything after the decimal point minus non-recurring things, and that is over 9s for each recurring number. There's two recurring numbers, so 2 9s, and a 0 for any non-recurring. Well, we have one non-recurring number in this one, which is our 3, and so we put a 0 in its place. So we can quickly say that the answer is going to be that. Now, I have a confession to make, which is that, you know, I picked this sort of shortcut up off someone else. This was not out of a book. Now, why does that make a difference? Well, I haven't seen any mathematical proof for this, and I haven't tried it with everything. So maybe I'll get round to it one day, but probably not. But for now, it works for everything that I've come across. So I would say, yeah, it's valuable. It's valuable to for the reasons I gave you before. But again, only use it as a check. Don't use it as you're working out, because you'll lose loads of marks. So that was a bit long-winded, but I hope that's been of some benefit. And again, as always, if you need clarification, just drop me a line, and as I'm able to, I'll see if I can help. So thanks for watching, and again, good luck in all your maths endeavours. See you soon.